the heart of an unassuming factory in Dayton, Ohio, a man with ink-stained hands and a mind that refused limits stared at a chalkboard covered with equations that seemed to defy reality itself. The world believed that propeller design had reached its peak, that airspeed and thrust were bound by the immutable laws of physics, and that American fighters of 1941 could go only so fast. Yet, in a small lab surrounded by hum of machinery, the engineer sketched curves that twisted, bent, and rotated in ways no one dared to try. Outside, test pilots were frustrated. Fighters lagged behind enemy aircraft. Dogfights were lost to mere fractions of seconds, and the skies over Europe and the Pacific demanded speed, precision, and courage that conventional design could not provide. This man, whose name would soon become legendary among aviators, was convinced he could build a propeller that not only cut through air, but cut through the very limits of human expectation. Every line he drew was calculated, yet it seemed like madness. Colleagues whispered, calling it impossible, while bureaucrats dismissed it as fantasy. Yet the engineer pressed on, fueled by vision, obsession, and a relentless refusal to accept what was considered unchangeable. He studied every blade, every angle, every pitch. The physics of air, the density at different altitudes, the subtle vibrations that could tear metal from a fuselage, nothing was overlooked. He experimented with materials, metals that were lighter yet stronger, laminates that could withstand tremendous torque without warping, coatings that reduced drag in ways science hadn't fully explained. Wind tunnels became cathedrals of innovation, the roar of fans a hymn to potential. Models whirred at thousands of RPMs, sensors capturing minute deflections and vibrations, and still he refined, recutting the pitch, altering the camber, testing shapes that seemed absurd, yet, when plotted against aerodynamic theory, suggested that they might work. Engineers from nearby factories came to watch, some shaking their heads, some secretly taking notes, but no one dared to touch the prototype. It was sacred, a marriage of math and intuition, genius and obsession, courage and audacity. Outside the lab, fighter pilots grew restless. Curtiss P-40s and early P-38 Lightnings could barely outrun enemy Messerschmitts and Zeros. The war demanded more speed, more climb, more maneuverability. Each delay in innovation meant lives lost in the air, squadrons outgunned, and campaigns slipping through the fingers of Allied command. Commanders despaired. Engineers questioned their own understanding of propulsion, and the man in Dayton pressed on, believing that a single breakthrough in propeller design could rewrite history. In secrecy, prototypes were fitted to test aircraft. The first flights were terrifying. Vibrations tore through the fuselage, sensors recorded readings beyond safe tolerances, and pilots nearly blacked out from G-forces caused by sudden acceleration. Yet, when the propeller stabilized, when the engine coughed and then roared with newfound fury, the aircraft leaped forward, slicing through air like a blade. Airspeed readings climbed steadily, 10, 20, 30 miles per hour more than conventional designs, and with each successful run, the engineer grinned. Knowing that the impossible was no longer theoretical, but the breakthrough didn't come without sacrifice. Materials failed, causing catastrophic in-flight incidents, wind tunnel blades shattered under extreme stress, and entire prototypes were scrapped. Yet every failure yielded data, every catastrophe refined understanding. The team of engineers, once skeptical, became disciples, adjusting calculations, reinforcing blades, and learning secrets of airflow that even textbooks had ignored. Slowly, incrementally, the propeller design evolved. Each iteration brought a new whisper of hope, a promise that Allied fighters could chase enemies they had previously only glimpsed in terror. Reports trickled in from test pilots. Climb rates improved, acceleration increased, turning radius enhanced slightly and at high altitudes. Engines coughed less, vibrations diminished, and speeds surged past anything previously deemed safe. The world outside Dayton remained unaware of the storm brewing. Enemy reconnaissance reports noted that new American fighters were vanishing into the horizon faster than expected. Pilots who had flown dozens of combat sorties swore that aircraft felt different, lighter, more responsive, hungrier for air. Yet no one knew the secret lay in the whirling, spinning miracle crafted by one obsessive engineer who refused to accept conventional wisdom. The propeller wasn't just metal, it was a manifesto, a declaration that limits were made to be challenged, and victory required vision beyond rules and calculations. And then came the day of reckoning. a prototype fitted to a P-51 Mustang, the sleek fighter that would become legendary. The pilot, briefed but unaware of the exact changes, throttled up. The engine roared, the aircraft leapt down the runway, and in moments, the speedometer climbed past numbers no American fighter had ever recorded. The wind screamed in the pilot's ears, the propeller hummed a metallic song of defiance, and for 1 minute the impossible became tangible, real, undeniable. Allied observers on the ground nearly fell backward at the reading, an increase of over 100 miles per hour. The Mustang soared with an agility and speed that stunned engineers, pilots, and commanders alike. Reports would later note that this single propeller design changed the dynamics of air combat across multiple theaters, allowing Allied pilots to engage enemies on their terms for the first time. But that was only the beginning. When enemy spies finally glimpsed the secret propeller, the reaction was disbelief, panic, and an urgent attempt to catch up, a race that would alter the skies forever. As the first P-51 Mustangs equipped with the revolutionary propeller rolled off the assembly lines, Allied commanders could hardly believe the reports flooding in. Flight logs recorded unprecedented climb rates, acceleration surges, and maximum speeds that exceeded all previous calculations. In the hands of veteran pilots, the aircraft now leaped off runways with a force that rivaled rocket launches, its nose rising sharply as the newly designed propeller sliced through air like a sharpened blade. Test pilots reported that maneuverability had improved dramatically, especially at high altitudes where previous designs struggled with drag and air density. The propeller's twisted, precision-engineered blades created lift and thrust in ways that defied conventional understanding, channeling airflow with uncanny efficiency. Radar operators noticed the change almost immediately. Allied aircraft appeared and disappeared over the horizon faster than anyone had anticipated, leaving both enemy observers and frontline soldiers struggling to track them. Enemy reconnaissance soon revealed the anomaly. Luftwaffe intelligence officers, already stretched thin by the rapid industrial output of American factories, were baffled by reports of fighters that outpaced every known German aircraft. Messerschmitt pilots described engagements with Mustangs where their own FW-190s and Bf-109s simply could not catch the target. Written reports contained repeated phrases: impossible speed, ghostly maneuvering, unreal acceleration. Germany's engineers and strategists were forced to reassess their entire understanding of aerial combat. The term impossible propeller began circulating in clandestine communications. Whispers of advanced American technology spread from Berlin to the front lines. Panic began to take root not just among pilots, but within the Reich's technical bureaus, who realized that catching up required breakthroughs that they could not instantly produce. Meanwhile, back in the United States, test flights continued with extraordinary attention to detail. Engineers recorded vibrations, torque, and airflow patterns meticulously. Early flights were perilous. Some aircraft suffered structural fatigue from the sudden acceleration, and in a few cases, the airframe twisted dangerously during extreme maneuvers. But each near failure provided invaluable data. Engineers learned to balance the torque produced by the propeller with the aircraft's weight distribution, fine-tune pitch angles for maximum efficiency, and reinforce key stress points in the fuselage. Each incremental improvement transformed the Mustang from a fast aircraft into a lethal predator of the skies. By the time the first squadron was deployed overseas, the propeller's design had already saved countless lives during training flights, cutting mission times and allowing pilots to avoid enemy flak zones more effectively. The first real combat demonstration was nothing short of spectacular. Over the skies of North Africa, Mustangs equipped with the new propellers engaged enemy fighters during reconnaissance missions. Reports from squadron leaders described breathtaking sequences. German fighters attempting to intercept the Mustangs found themselves outrun repeatedly, struggling to keep pace as the American planes climbed higher and accelerated faster than anticipated. Dogfights unfolded in ways previously considered impossible. Pilots who had trained for years suddenly realized that speed and climb rate had become tactical advantages that redefined engagement strategies. The Mustang could dictate the terms of combat, striking with precision, evading retaliation, and retreating before enemy gunners could adjust. In one particularly dramatic sortie, a pair of Mustangs encountered a formation of 8 FW-190s. The German pilots immediately attempted to outmaneuver the Americans, banking and diving at speeds that would have overwhelmed older Allied fighters. Yet the Mustangs, propelled by the engineer's revolutionary design, responded flawlessly. With a combination of high-speed turns and vertical climbs, the two American planes evaded the entire formation, returned fire with lethal accuracy, and exited the engagement with no damage sustained. Debriefings recorded shock and awe. Enemy pilots had no comprehension of how such small craft could possess such velocity and agility. The term ace killer began to emerge in field reports, describing the propeller's indirect impact on combat effectiveness. It was not just a piece of metal, it was a psychological weapon. The psychological effect on enemy pilots cannot be overstated. For months, German forces struggled to understand how Allied aircraft seemed to vanish and reappear unpredictably. Intelligence officers reviewed captured wreckage, interrogated prisoners, and even attempted to reproduce the propeller's geometry from photos and sketches, yet every effort fell short. Engineers in Germany began experimenting with complex blade curvatures and novel materials, but wartime shortages of aluminum and high-grade alloys hampered development. While Allied production continued unabated, the Luftwaffe found itself increasingly outmatched in both speed and maneuverability. Reports began to note rising panic among frontline German pilots, many of whom refused to engage Mustangs directly, opting instead to attack less capable aircraft. The propeller's design had effectively rewritten the air combat equation. By mid-1943, Allied command had begun reassigning Mustangs equipped with the propeller to critical missions over occupied Europe. The aircraft's newfound performance enabled long-range escort missions, reconnaissance flights, and tactical strikes that had previously been too dangerous. Pilots reported unprecedented confidence, knowing that their aircraft could outrun interceptors and climb faster than enemy formations could respond. Air superiority shifted incrementally as the numerical advantage of Axis aircraft was neutralized by the tactical flexibility granted by the new propeller. The design had not only increased top speed by 100 MPH, but had transformed strategy, morale, and survivability in ways that no single engine or armament could achieve. Yet even as the Luftwaffe scrambled to respond, the greatest secret of the propeller remained hidden. A subtle twist in its blade design that would allow Allied fighters to perform maneuvers previously thought physically impossible. A revelation that would change the course of the air war forever. By the time the first full-scale flight tests were complete, the engineer had uncovered the secret that made his propeller truly revolutionary, a subtle, nearly imperceptible twist along each blade that allowed the Mustang to slice through the air with unprecedented efficiency. At first glance, the blades appeared ordinary, crafted from polished aluminum and reinforced with high-strength steel cores, but closer inspection revealed a complex curvature that varied along the length of each blade. The pitch wasn't uniform, the camber subtly changed, and the tip of each propeller blade was twisted in a way that most aeronautical textbooks dismissed as impractical. Conventional engineers had long believed that any significant twist would cause vibrations, reduce thrust, or risk catastrophic structural failure. Yet through hours of wind tunnel tests, iterative modeling, and daring real-world flights, it became clear that this impossible twist amplified thrust while reducing drag, a combination that effectively bypassed the traditional limitations of propeller aerodynamics. This innovation worked because it redistributed airflow along the blade, keeping the air attached longer and reducing turbulence at critical points. At the root of the blade, where torsion and centrifugal force were greatest, the design minimized strain while optimizing lift. Toward the tip, the twist accelerated airflow, producing additional forward thrust without increasing engine load. Engineers calculated that this configuration alone could improve efficiency by up to 15% at high speeds, translating directly into higher top speed and faster climbs, precisely the performance gains that pilots desperately needed to survive against advanced enemy fighters. The genius was not merely in theory, it manifested in raw numbers on the speedometer as test pilots repeatedly recorded 100 MPH gains over older propeller designs without sacrificing stability or safety. Early test flights were harrowing. Pilots encountered unusual vibrations as the propeller reached higher RPMs, and a few prototypes suffered minor blade fatigue under extreme acceleration. Each failure, however, provided critical data. Engineers documented stress points, refined the metallurgy of the blades, and improved the balance to prevent resonance at high speeds. The result was a propeller that combined mechanical durability with aerodynamic perfection, a delicate harmony between science and art. This harmony allowed the Mustang to climb faster, maneuver more responsively, and accelerate with a sudden burst that left enemy aircraft struggling to react. Once the prototype was mounted on operational Mustangs, combat exercises revealed the full scope of the innovation. During high-speed dogfights over European airspace, pilots could now execute maneuvers previously deemed impossible. Tight vertical climbs, abrupt reversals, and sustained high G-turns became feasible without losing thrust or stalling the aircraft. Enemy pilots, accustomed to chasing older Allied fighters, found themselves consistently outrun and outmaneuvered. Reports from field commanders described a new tactical reality. One Mustang could engage multiple enemy fighters sequentially, dictating the terms of combat and disengaging at will. The subtle twist of a single propeller blade had transformed air combat dynamics, turning numbers, firepower, and positioning into secondary considerations compared to sheer speed and maneuverability. The engineers' work also had long-term implications beyond immediate combat performance. The geometry of the propeller allowed for better high-altitude efficiency, meaning Mustangs could escort bombers deep into enemy territory without exhausting fuel prematurely. Pilots noted smoother engine operation, reduced vibration, and decreased propeller noise at cruising speeds, all of which improved operational endurance and crew comfort. This combination of speed, climb rate, and efficiency meant that the Allies could maintain air superiority over enemy territory more reliably than ever before, fundamentally shifting strategic planning for air campaigns. Meanwhile, intelligence analysts and enemy engineers scrambled to understand the design. German reconnaissance photos captured the modified propellers, but without wind tunnel analysis and the detailed metallurgical insight available only to the engineers team, replicating the performance proved impossible. Field reports from Luftwaffe pilots included phrases like unbelievable acceleration and aircraft moves like a phantom, underscoring the psychological impact of the innovation. The twist wasn't just a mechanical improvement, it was a game changer affecting strategy, morale, and the perception of Allied air power. Yet even as the propeller's twisted blades carved new paths through the sky, a hidden flaw remained, one that only combat would reveal, a secret challenge that threatened to undo the impossible gains and test the resolve of pilots and engineers alike. As the new propeller design moved from wind tunnels to operational aircraft, the team quickly realized that extraordinary performance came with extraordinary risk. The Mustang, now equipped with the impossible propeller, had reached speeds and climb rates that pushed the airframe and engine far beyond previous tolerances. During early test flights, pilots reported extreme vibrations at high RPMs, sudden torque-induced yaw, and occasional structural resonance that rattled control surfaces. While the blade geometry provided unprecedented thrust, it also introduced aerodynamic forces that few had anticipated, creating a narrow window between peak performance and catastrophic failure. One test pilot later described the sensation. It felt as though the aircraft had a mind of its own, surging forward, twisting, fighting against me, exhilarating and terrifying in equal measure. The danger wasn't limited to vibrations. Engineers observed that under sustained high-speed maneuvers, localized stress at the root of the blades could initiate microfractures, which risked blade separation mid-flight, a fatal event. To mitigate this, metallurgists experimented with advanced aluminum alloys and reinforced steel cores, carefully balancing strength and weight. Propeller hubs were redesigned to distribute torque more evenly, and detailed inspection protocols were instituted after each flight. Even with these precautions, the margin for error was slim. A single miscalculation in RPM, air density, or engine output could trigger catastrophic consequences. The program teetered on a knife's edge, and at times, top brass seriously considered halting production until safety could be guaranteed. In one dramatic test, a Mustang pilot reached near-record speeds during a climb, only to experience an abrupt propeller-induced oscillation. The aircraft lurched violently, control surfaces shook, and the canopy rattled with a roar that echoed throughout the fuselage. The pilot fought desperately to stabilize the plane, and after what seemed like an eternity, he brought it back to the runway with only minor damage. Engineers immediately disassembled the propeller, examined each blade under high-magnification cameras, and discovered tiny stress fractures invisible during routine inspections. These small flaws, multiplied across rotational forces, explained the terrifying behavior. The solution required an iterative redesign of both blade geometry and material composition, pushing the limits of wartime manufacturing. Meanwhile, Pilots trained intensively on the new aircraft to adapt to its unique flight characteristics. Unlike previous fighters, the Mustang now demanded precise handling. Abrupt throttle changes, sharp banking, or sudden dives could produce unexpected torque effects. Training manuals were rewritten to include the new physics, and instructors emphasized smooth, calculated maneuvers. Pilots quickly realized that the propeller's performance was a double-edged sword. It could deliver unmatched speed and climb, but mismanagement could prove fatal. Reports from squadron debriefs highlighted both the exhilaration and the fear, a fighter that could evade any pursuer, yet required absolute respect from its pilot. Despite the risks, the advantages were undeniable. Allied forces began to plan missions around the propeller's capabilities, using Mustangs to escort bombers at altitudes and speeds that previously left crews vulnerable. Early combat sorties proved that the aircraft could outpace any Luftwaffe interceptor, and the morale boost among Allied pilots was immense. However, engineers remained vigilant, constantly monitoring wear patterns, stress distributions, and minor deformations in the blades. Each flight was logged meticulously, every anomaly dissected to prevent the disaster that had nearly grounded the program. The hidden danger also affected maintenance protocols. Ground crews were trained to inspect the propeller blades for microfractures, balance the assembly to precise tolerances, and replace components after limited flight hours, far more rigorous than with conventional fighters. These procedures required intense labor and skill, yet they were essential to prevent catastrophic failure. The engineers' team worked around the clock, refining inspection methods, testing new alloys, and pushing production standards to unprecedented precision. What had begun as a daring aerodynamic experiment had become a complex operation balancing engineering genius with practical safety. Yet even with all precautions, the looming threat of in-flight propeller failure created suspense among pilots and commanders alike. Every mission carried a silent risk. Could the blades withstand the stresses of combat, or would they fail at the worst possible moment? The tension became part of the Mustang's mystique, the combination of extreme performance and calculated danger that defined the aircraft's revolutionary impact on the air war. Allied commanders understood that mastery of this impossible technology required skill, courage, and constant vigilance, making the Mustang not only a machine, but a test of human ingenuity and resilience under pressure. But the greatest surprise was yet to come. When the new propeller design faced its ultimate trial in real combat against experienced Luftwaffe aces, the results were more than shocking. They were revolutionary, forever altering the skies over Europe. When the first Mustangs equipped with the revolutionary propeller arrived over the European theater, the skies themselves seemed to change. Pilots reported a sensation unlike anything they had experienced. Instantaneous acceleration, steep climbs that defied expectation, and a top speed that left enemy interceptors struggling to maintain contact. Within hours of deployment, reports filtered back to Allied command describing unprecedented performance. Squadron leaders were awestruck. The aircraft could dictate engagements, choosing when to fight and when to retreat, rendering previous tactical disadvantages nearly irrelevant. The propeller's twisted blades didn't just move air. They transformed strategy, allowing pilots to control the tempo of combat in ways that had never been possible before. On one of the first sorties, a group of Mustangs escorted a formation of B-17 bombers deep into enemy territory. German fighters, anticipating an easy interception, scrambled to engage the convoy. Almost immediately, it became clear that they were unprepared for the new aircraft. The Mustangs climbed rapidly, maintaining speeds that far exceeded the Luftwaffe's expectations. Enemy pilots described seeing the American fighters appear and disappear like phantoms, gaining altitude, strafing attackers, and retreating before a counterattack could be mounted. Observers noted that these maneuvers were made possible by the propeller's efficiency, which amplified thrust without sacrificing stability or control. The effect on morale was profound. Allied pilots who had previously faced daunting odds against superior aircraft suddenly found themselves in control. Confidence surged across squadrons, and commanders began planning missions that would have been considered reckless just weeks earlier. Dogfights shifted from desperate survival to calculated offense, with pilots exploiting the Mustang's new speed and climb rate to engage multiple enemies sequentially. Ground crews noted that sortie completion times decreased, fuel consumption remained manageable despite higher speeds, and aircraft returned with minimal stress damage thanks to careful engineering oversight. The Luftwaffe, by contrast, struggled to adapt. Experienced German pilots, confident in the performance of their Messerschmitts and Focke-Wulfs, were suddenly encountering aircraft they could neither catch nor predict. Tactical doctrines developed over years proved insufficient. Intercept patterns failed, climb rates were inadequate, and pilots experienced frustration and shock in repeated encounters. Intelligence reports documented growing panic and confusion. The American Propeller had produced aircraft that could escape pursuit, re-engage at will, and survive engagements previously considered suicidal. In one notable engagement over northern France, a squadron of 10 Mustangs faced 18 Luftwaffe fighters. Conventional wisdom would have dictated a defensive posture, but the Mustangs' performance turned the tables. Climbing above the enemy formation, the pilots utilized vertical maneuvers and rapid dives made possible by the propeller's efficiency to strike decisively. Within minutes, several enemy aircraft were neutralized or forced to retreat, with no losses to the Americans. Debriefings later described the encounter as miraculous and impossible by conventional rules of air combat. The results spread quickly, reinforcing the Mustang's reputation and the engineer's revolutionary design as a game-changer. Beyond individual skirmishes, the propeller's impact reshaped entire campaigns. Long-range escort missions, previously constrained by aircraft limitations, became feasible with minimal fuel penalties. Strategic bombers could penetrate deeper into enemy territory, protected by fighters that could outperform any interceptor. Reconnaissance flights reached farther distances, gathering intelligence with reduced risk. Even supply drops and tactical air support benefited, as the Mustang could arrive, deliver payloads, and depart with unmatched speed and precision. The propeller had not only enhanced the aircraft, but had multiplied the effectiveness of the entire Allied Air Force. Moreover, pilots adapted to exploit the new capabilities in creative ways. Swinging maneuvers, high-speed climbs to gain altitude advantage, and aggressive hit-and-run tactics became standard. Veteran pilots remarked that the aircraft seemed alive, responding instantly to commands and forgiving only to those who respected its limits. The blend of extraordinary speed, climb, and control redefined the doctrine of aerial combat. Where previously numerical superiority might dictate the outcome, now tactical ingenuity and the advantage of engineering mastery dominated. The psychological effect on the Luftwaffe was equally dramatic. German airmen reported feelings of helplessness when engaging Mustangs, struggling to maintain formation as American fighters accelerated past them, climbing vertically with ease or disappearing beyond visual range only to return for another pass. Commanders began redesigning engagement strategies, but the pace of Allied innovation outstripped their ability to respond. The propeller had introduced a new variable, the sheer unpredictability and superiority of speed, which disrupted centuries of accumulated tactical knowledge and forced a re-evaluation of air combat principles in real time. Yet even as the Mustangs dominated the skies, a new challenge loomed. Enemy engineers and strategists were racing to uncover the secret of the propeller, a secret that, if deciphered, could neutralize the very advantage that had redefined air combat. As Allied Mustangs with the revolutionary propeller tore through the skies, German engineers and Luftwaffe strategists faced an unprecedented crisis. Reports of American fighters outpacing their best interceptors reached Berlin with alarming frequency. The secret, hidden in the subtle twist and geometry of a single propeller, was beyond their immediate understanding. Desperate to restore parity, Germany mobilized its finest minds in a frenzied attempt to replicate or counter the innovation. Airframe designers analyzed wreckage from downed Mustangs, metallurgists studied captured propeller fragments, and aerodynamicists scoured photographs for any clue of the blade's subtle curvature. Yet every effort fell short. The technology was not merely about materials or engine power. It was about the fusion of precision engineering, blade twist, airflow control, and metallurgy, a synthesis that had emerged from one engineer's obsession and relentless experimentation. As the Luftwaffe scrambled to respond, Allied pilots exploited the advantage mercilessly. In dogfights over Normandy and northern France, Mustangs continued to outmaneuver enemy aircraft, dictating the tempo of engagements with near impunity. The propeller allowed sustained acceleration in climbs that traditionally would have stalled earlier fighters, enabling pilots to strike decisively and disengage before retaliation. Squadron reports detailed encounters where outnumbered Americans decimated formations of Messerschmitts and Focke-Wulfs, leaving observers and adversaries alike astonished. The Propeller had effectively rewritten the rules of aerial warfare. Speed was now the ultimate weapon, and agility amplified by engineering precision had become an unstoppable force multiplier. Meanwhile, German countermeasures began to emerge, but too late to be decisive. Engineers attempted new alloys, unconventional blade designs, and incremental aerodynamic improvements, but none approached the efficiency and subtlety of the original American propeller. Some prototypes failed spectacularly in testing, with vibrations tearing apart engines, while others produced only marginal gains insufficient to match the Mustang's performance. German pilots faced a grim reality. Their aircraft could no longer engage American fighters on equal terms, and strategic planning had to be adjusted to avoid direct confrontation. The psychological impact was as severe as the physical. Fear and frustration spread through squadrons, eroding confidence even among experienced aces. The engineer in Dayton, meanwhile, remained largely unknown to the world. His propeller had transformed air combat, but few understood the genius behind it. Pilots praised the aircraft, command celebrated the tactical advantage, and Allied bombing campaigns achieved new heights of success. Yet the creator's identity remained obscured by wartime secrecy. His obsession with curves, material science, and minute aerodynamic shifts had created a weapon that could decide battles without firing a single round. A marvel of pure engineering, innovation, and foresight. In the skies above Europe, Mustangs continued their relentless campaign, striking with speed, precision, and efficiency. Enemy formations hesitated, regrouped, and often fled, unable to match the newfound acceleration and climb rates. The engineer's design had done more than increase speed. It had rewritten the balance of power in the air. Allied pilots gained confidence, morale soared, and enemy strategies collapsed under the weight of a technological leap that seemed almost magical. Each sortie reinforced the legend. A single propeller, impossible in concept, had delivered victory through ingenuity, courage, and unwavering determination. The final confirmation of success came in cumulative data from months of combat. Allied aircraft achieved mission success rates previously considered unattainable. Enemy interception rates dropped dramatically. Casualty ratios shifted decisively in favor of the Allies, and all of it traced back to a subtle twist on a metallic blade, an impossible idea that no textbook had ever described and no adversary could replicate. The skies had been forever changed, and yet, hidden in every Mustang's roar, in every climb that defied expectation, remained the silent testament to one man's obsession, a single engineer who proved that the impossible was just the beginning.